Before we discuss the air standard analysis of Otto cycle, let me discuss what assumptions are made when you start with the analysis for the Otto cycle, diesel cycle, dual cycle, whatever. Okay, so there are certain assumptions which are made in the air standard cycle analysis, and those assumptions make it as a very ideal kind of analysis. So, what are those assumptions? So, in the actual engines, you know that the working fluid is actually, if it's a petrol engine, the working fluid is a petrol air mixture before combustion, and the working fluid is the products of combustion after the phenomena of combustion. Okay, this is actually happening in the engine, but in the air standard analysis, we don't consider that there is a mixture of gases. We say that the working fluid is only ideal gas. It's an ideal gas. Okay, we do not consider the air fuel mixture as a working fluid. Then you know that the real processes which are happening in the engine, be it a compression process, expansion process, the heat addition process, all these real processes which are happening in the engine, they are irreversible. Okay, there is a lot of friction, there are a lot of losses, but in the assumptions of the air standard analysis, we neglect all these irreversibilities and we say that all the processes in the air standard cycle, they are reversible processes. They are reversible processes. Okay. Then you know that in the petrol engine, the combustion happens because you are igniting the fuel using a spark plug. Okay, or in the CI engine, diesel engine, you know that you are first compressing the air and then there is an injection of the fuel, and because of the self-ignition temperature of the diesel, the phenomena of heat supply happens. Okay, that is, there is a combustion phenomena. But in the air standard analysis, we assume that the heat is supplied not by combustion but from the source. And as you know that source is a very theoretical concept whose temperature is high temperature and its temperature will not change even if there is a heat supplied from that source. So we are assuming that the heat is not supplied from combustion but it is supplied from a source. Similarly, in the real life, the heat is rejected to the surroundings. Okay, and in this analysis, air standard analysis, we assume that heat is rejected to the sink, that is a constant temperature sink. In the real engines, you know that there are a lot of heat losses. In the air standard analysis, we assume that there are no heat losses. No heat losses happen. Okay, zero heat losses. And finally, you know that the specific heat, which is the ratio of the specific heat, which is Cp and Cv. Cp is the specific heat at constant pressure, and Cv is the specific heat at constant volume. And the ratio of the two, which is the adiabatic index Cp by Cv, they vary with respect to temperature. But in this analysis, in the air standard analysis, we assume that this specific heats, they remain constant, the value remains constant, unchanged, irrespective of the temperature. And we also assume that they have a very standard value, the values being equal to that of the ideal gas. Means we assume that Cp of the working fluid is 1.005 kilojoules per kg Kelvin. The specific heat at constant volume is 0.717 kilojoules per kg Kelvin, and the adiabatic index is 1.4. So these are all assumptions which we make in the air standard analysis. Now when you make such assumptions, when such kind of assumptions are made, the value which we are going to get, which is nothing but the air standard efficiency which we are going to calculate, would be farther from the reality. It won't be the actual value, right? The value which you would be getting would be much, much higher. Then why do we do this analysis? We do this analysis because it gives you important insights. For example, when you do the Otto cycle analysis, we get a relationship between the compression ratio and the efficiency of the engine, okay, which we are going to derive shortly. If we do the diesel cycle analysis, air standard analysis, we get a relationship between the cutoff ratio, the compression ratio and the efficiency. Likewise. So it means that even after making such assumptions, we do get certain relationships which would be helpful in the design of the engine, actual engines. Okay. So though it is very simplistic to assume all these things, the simplifications will give you a higher value of efficiency than the actual value, but still this analysis is useful because it gives us important insights. So in the next class, we are going to do the year standard analysis of the Otto cycle, where I would be deriving an expression for the year standard efficiency of the Otto cycle. Thank you.